Alright, welcome back to my YouTube channel. So today we'll solve a couple of problems on the damped harmonic motion. So we're calling this part 1 because we're still going to solve a couple of problems in subsequent videos. So let's dive in deeply into the questions we're given. So this is question 1 and we are asked to find the particle velocity. So we're given the displacement of the particle, which is given by this expression, and we want to find the particle's velocity. So we should know that x dot is given by this. So what do? We simply just differentiate it. So if we differentiate this function, we have that x is actually equal to d. X dot is equal to the x over the t. So that's what we did, and we use the product rule, y equals uv. So y dot is equals to u dv plus v du, where d is equal to d over dt in this case. So that's what we did. So if we substitute our parameter for 2, which is the time, we'll end up having this as x dot, which is our velocity, particle velocity. So let's call it vp equal to. So this is vp, particle's velocity. For question 2, we're asked to determine the logarithmic decrement. So remember that our logarithmic decrement is given by this. Actually, beta is our exponential decay constant. It's given by gamma over 2. And this whole expression is simply b over 2m. So first of all, we need to look for gamma. So from here, if we make gamma the subject of the formula, we're going to have that gamma is this. And of course, we can substitute it for beta because beta is gamma over 2. So 2 should cancel 2, and we end up having this expression for beta. So if we expand that by pushing omega d inside the square root, we're going to actually have a square root of omega naught square over omega d square minus omega d square divided by omega d square. So that's what we are going to have is our square root. So this is going to omega d here is going to cancel omega d here, giving us 1. So we finally have this expression here. So we can still replace omega naught to be 2 pi f naught, and similarly we can do same for omega d. So finally get that expression of which, if we substitute f naught, which is our natural frequency, 20 cycles per second, and fd 16 cycles per second, we end up having 3 over 2 pi. So moving on to question 3, we are asked to find the quality factor. So how do we determine the quality factor? This is our expression we have given earlier, omega d over gamma, and omega d is 2 pi f of d, and gamma is 2 over tr. So from here, if you do the mathematics, you should have 200 pi. So moving on to number 4, we have to show this relationship. So before we can show this relationship, we first of all need to know our formula for our energy, and this is our formula for our energy. So this is formula for our energy. This is our initial energy at t equals to 0. So we have to find the time taken, which is t half, for the energy to decay to half. So it means find the time for e of t, the energy at time t, to become 1 over 2 e of 0. So in place of e of t, we have to substitute half e of 0. And of course, this can cancel this. We end up having this expression. And if we make t half subject, we finally have this expression. So what the only thing I did, I actually replaced gamma here by saying gamma is 1 all over tc for this case. So if you replace that, you have the final expression. So lastly, number 5, we're given this. It's a consider a damped harmonic motion or oscillation consisting of a mass of 150 grams attached to a spring of stiffness and mechanical resistance. We are asked to find the exponential decay constant. We were given the displacement of the particle. So let's dive in deeply. Let's solve. We can solve this by saying, it's a very simple question, by saying question A. So from question A, the exponential decay constant beta is equal to rho(n) all over 2m, which is the same thing as b over 2m. So put your b, the b we're given is 3, 2 times, convert your mass to kg, which is 0.15. So 0.15, I think this answer should become 10, if I'm not mistaken. So 2 times 0.15 is 0.3. So 3 over 0.3 should be 10. So for B, we're asked to find the natural angular frequency omega naught without damping. So omega naught will be equal to square root of k over m, which is the square root of k in this question they gave to us is 275 divided by m is 0.15. So you can press this expression and tell us what you get later on by your own. So C is the natural angular frequency, omega d. Omega d is simply, how do you get your natural angular frequency? Simply square root of omega naught square minus gamma square over 4. So if you substitute for omega naught square and substitute for gamma, you already know what gamma is. Gamma is b over m. If you put the final answer, whatever you get is omega d. So D, it said given the initial condition, pick a good value. So how do you do this? You can do this by substituting the parameters we are given. You said x of t here is 0 when t is 0. So if you put that here into this expression here, you're going to have 0 is equal to a exponent raised to power 0, because beta times 0 is 0, sine of omega d times 0, t0 is 0. So I left with phi, and if we make phi the subject, phi is going to still give us 0 degrees. So that's a good approximation. It's a good one. So for E, we're asked to find, so determine the value of the displacement amplitude A. So given another initial condition like this, when t is 0, u of t is 25. It means that in this equation, substitute when t is 0. Let's see what u will give to us. Use 25 when t is 0. So 25 should be equal to, so we have A times omega d. Now you notice that everything here will give us 1. Omega d times t is 0. So omega d times d is 0. So everything here again will give us 1. Cosine of everything there will give us 1. And every expression here will give us 0. Why? Because sine of omega t is 0. Omega dt is 0. And phi is also 0. 0 plus 0 is 0. So sine of 0 will still give us 0. And it blows up to the entire expression to 0. So we left with 25 is equals to A times omega d. And of course, A should be equal to 25 divided by omega d. So you can substitute the expression for omega d. And lastly, F, we're asked to find the period of the damped motion. So the period of the damped motion should be T. Let's call it TD. TD is equal to 2 pi over omega d. So you can put in your expression and check for the final answer you get. So see you on next class for some further examples again, so you can master how to solve several problems on damped harmonic motion. Thank you for watching.